research methods for psych. Remember that this particular area of study goes across both Unit 3 and Unit 4, so you may need to watch this video a few times. Also remember that research methods will be assessed on every one of your SACs for Unit 4, so definitely an area of focus. Let's get into it. Well, it decides to work. Okay, so basically when we do research in psychology, there are two different ways of doing research. In class at the moment, we've been focusing on the experimental method, and the experimental method is when we actually actively manipulate one particular variable, the independent variable, to see if it affects the dependent variable, what change it has on it. The other way that you can do study is to basically just look at relationships that already exist between variables. So an example of an experiment is seeing whether lollies affects your performance in an IQ test. So the independent variable would be the lollies, and you would expect one group to have lollies and one group not to have lollies. And then the dependent variable would of course be the score that you get on your IQ test. Correlational study, an example would be height and weight. So for instance, you take a group of people, you measure their height and their weight, and you expect there to be a relationship between them. Generally, the taller you are, the more that you would weigh. So you would think that would be a positive correlation. So generally in psych, we talk about the experimental method, but it's good to know that correlational studies occasionally are done as well. Okay, so when we do the experimental method, the researchers actually manipulate the independent variable. And you can see there I've written down some definitions of both the IV and the DV. So the independent variable is independent, free to change, whereas the dependent variable is dependent upon the manipulation of the independent variable. So it will change depending on the independent variable. You need to get very good at identifying the IV from the DV. Okay, once we've got an idea of our experiment and what the IV is and what the DV is, generally we expose the experimental group or experimental condition to the IV. So if we go back to lollies and IQ, the experimental group would have lollies present and the control group would have the IV absent, so no lollies. And basically you have the control group there to provide a comparison to see whether the lollies actually make a difference. Unfortunately, when we do experiments like this, we know that other variables, apart from the IV, the independent variable, often will impact on the dependent variable. And these are usually called extraneous variables. So what we mean by that is, obviously, whether you eat lollies or not is not the only thing that's going to affect how you do on an IQ test. So the other things like your level of your IQ, perhaps the amount that you read, perhaps your level of interest and motivation, these are all extraneous variables, extra variables that have an unwanted effect or could have an unwanted effect on the actual experiment. And if you identify your extraneous variables and eliminate them, then generally you carry out a really good piece of research. However, if you don't identify your extraneous variables at the start of the research, at the end of the research, if you've let them affect your results, they become confounding variables. So an extraneous variable has the possibility to confound or confuse the outcome, but we talk about them becoming confounding variables when it actually has an unwanted effect after the experiment has been carried out. So for instance, IQ coming in could be an extraneous variable, but if we've decided to test all of our students and they all had equal IQ, we've eliminated it and therefore it didn't become a confounding variable. However, if we didn't test for it before the experiment, we knew about it, it's an extraneous variable, we let it affect our experiment, it confounds the results, so therefore it's being called a confounding variable. There are lots of potential confounding variables or possible extraneous variables, and these are things like individual participant differences. So anytime we do research, we need to be very aware of this, and obviously we look at sampling procedures to ensure that the participant differences are minimum. The placebo effect, which we'll go through in the next slide, but that can be controlled using a single blind experiment, and I'll explain that later. The experimenter effect, which again is explained in the next slide, but that can be controlled as well. Order effects, they can be controlled. Artificiality, now this is the one, the fact that, you know, quite often we do experiments in labs, so we can't always replicate real life situations. And unfortunately, that's just the fact of the matter, so we can't always control for this. And sometimes you find that experimenters, there's a numerous amount of experimenters doing the research, so therefore they might be giving different instructions to groups of people, and this can be controlled by giving them a script and making sure that everyone has standardised instructions. So these are just some possible things that can affect our experiments. So in a little bit more detail, so the placebo effect occurs when participants believe that something's going to bring about a change. So for instance, if I told the group that they were having lollies and it was going to make them much smarter, that alone, the belief that they may be smarter, can bring about the change in the dependent variable as opposed to the actual having the lolly. The experimenter effect is when the experimenter brings about the change. So for instance, if I told all the students that were having lollies that, you know, they were amazing and they've always got really good test results, so, you know, I'd assume nothing less from them. And I told the other group, the control group, that, you know, unfortunately they weren't very intelligent, that might affect the experiment as well. So that's me as the experimenter affecting the results. That's called the experimenter effect. Self-fulfilling prophecy, so that quite often occurs when, you know, people just go, oh yeah, I'm going to do really good or I'm going to do really bad, and surprise, surprise, they do exactly how they expected. An experimenter bias happens when the experimenter interprets the results incorrectly. So they've carried out the experiment really well, but then when they're writing up the experiment and making some explanations, that they put their own bias on that actual write-up of the research. So there's plenty of room for error, basically. Okay, please make sure that you know how we actually select participants for research. So this is called sampling, and we know that participants are called the sample, and the population is the larger group of interest, and we know that our sample should be representative of our population. We know that there are 3 different types of sampling: convenient sampling, random sampling, and stratified sampling, and please ensure that you know the difference between them. Once you've got your sample, usually we randomly allocate then to different groups, depending on which research design we're using. We'll go into that shortly. But you know, the most traditional method of getting a group, a sample, and then separating them into the control group and the experimental group involves random allocation, which basically means, you know, each participant had equal chance of being in either condition of the experiment. We will have had a practice of this in class, so hopefully you can relate it back to that example. We usually have a research hypothesis to start with when we do any experimental research. So this is basically just a general prediction about what we expect the relationship between the IV and DV to be. And even though I said it's a general prediction, it doesn't use general terms. So for instance, I couldn't just say lollies will raise people's IQ. I'd need to actually say what lollies. So for instance, was it barley sugar? Was it snakes? Was it Milky Ways? So, you know, and so also possibly Year 12 students who eat Milky Ways will do better on an IQ test than Year 12 students who do not eat Milky Ways. So that's the basic idea of research, of a research hypothesis. So just a general prediction, but we're trying to have specific terms in it. I know that sounds really contradictory, but we'll do a lot of practices of a research hypothesis in class. So don't stress too much about it and just try to get some of those notes down. Okay, an operational hypothesis is a much more detailed prediction of what's going to happen. And basically it's almost like a recipe. So whoever reads your operational hypothesis should be able to replicate your piece of research and know exactly what you did. So for instance, you can see there we've got a general research hypothesis that hypnosis is an effective method of giving up smoking. And if you then operationalize it, you've got it to adult smokers who regularly smoke 20 cigarettes per day and wish to give up will be more successful in reducing the number of cigarettes smoked to 5 per day as reported in the daily log when treated with 5 2-hour hypnosis sessions than an adult smoker who attempt to give up smoking without undergoing treatment. That is a really full-on sentence, but it tells us lots of things. It tells us that the people who were in the experiment smoked 20 cigarettes per day. It told us that we consider reducing it to 5 as a successful outcome. It told us that the people would have 5 lots of 2-hour hypnosis sessions, and the others wouldn't have any. It tells us that they will report to a daily log in terms of how many cigarettes they're having per day. So really, from that, we would be able to replicate this person's research. So operational basically just means a really in-depth hypothesis that clearly outlines the IV, the DV, and the population with whom we're actually testing. So the hypothesis should be the IV needs to be specific, the DV needs to be specific, the population needs to be outlined, it should be able to be testable, it should be an educated guess, precisely worded and expressed clearly. Again, we'll practice a whole heap of these in class. Okay, there are 3 different types of research designs that you can do. So once you've got your sample through convenient sampling, random sampling or stratified sampling, then you have 3 different options of how to carry out your research. So the repeated measures design basically means that whoever in your sample will actually be in all of the groups within your study. So again, if we stick with the lollies and IQ, that basically you would have 20 participants. One day you'd get them in, they'd all have lollies, then they'd all do an IQ test, you'd look at their results, and then another day you'd get them in and they'd all have no lollies, and then you'd look at their IQ test results on that day, and you'd compare them. So the same group of participants, and they're basically repeating every aspect of the experiment on each of the participants. The main benefit of this is because you're using the same participants, there's no individual differences. The main disadvantage is that because each person in the experiment is doing all the experimental conditions, they might just get better simply through practice. So maybe you just get better at the second IQ test because it's the second IQ test and not because of anything that the experimenter actually did. This can be eliminated using counterbalancing. Counterbalancing is very complex to explain, and I will do that in class. Okay, so this effect is called the order effect. So repeated measures is great to eliminate individual differences, but it does cause what we call the order effect. Matched participants design, this is where we keep participants in separate groups, but we try to match them on key characteristics. So perhaps you might have someone in group 1 that has an IQ of 120 who is female. That means that you would have to have someone who's female in group 2 with an IQ of 120. And each person you would try to match on a key characteristic that you think may affect the experiment. And basically then you carry out the experiment with your 2 matched groups, even though they are different people, they're matched on key characteristics. Quite good in that, again, it reduces individual characteristics. It doesn't cause the order effect, but it's actually quite timely and can be very hard to match people unless you've got twins. Twins are ideal for this particular study. Independent groups design is the most common kind of design because it's quite easy. So it basically just means randomly allocating participants to 1 or 2 or 3 groups, and they each do their own condition in the experiment. So it's random, it usually ensures that there's an even spread of participant characteristics and there's no order effects. Clearly, however, it means that we do have individual differences that we have to combat, and that could actually impact on our results. So they all have their benefits and limitations. You can also do a single blind or a double blind study. A single blind study is when the participants are unaware of whether they've been assigned to a particular condition. So they will come in, for instance, and just be asked to do something, and let's say they're drinking a substance this time. One group might have water, one group might have something that tastes like water, but perhaps it's got something else in it, and then we can test the effect of that other substance. Basically, the participant's unaware. This counteracts the placebo effect. In a double-blind experiment, both the participants and the experimenters are blind to the conditions, which means a third party has to come in and actually carry out the research on behalf of the experimenter. So basically, this gets rid of both the placebo effect and the experimenter effect as well. because no one in the actual experiment can affect it because they don't know what's happening. When we collect data, there are two different types of data we collect from experiments, and they are qualitative data and quantitative data. So qualitative data is quite often when we ask people about how they're feeling and they give us descriptions back. So that's quality data, very detailed, but it's very hard to summarise. Quantitative data is when information comes back in terms of numbers. So a score on an IQ test is quantitative data. Measuring someone's weight is quantitative data. So we tend to gather this information a lot in psych research because obviously it's very easy to summarise numbers as opposed to people's statements about how they're feeling. Statistics, once we actually get the research and the data, we then have to be able to display it, and we use descriptive statistics in psych to do this, very much like your maths. So we can use things like pie charts and histograms and mean, median, mode, and all of those descriptive statistics that you've learnt about, and they will help you summarise what you've found in your results. The other thing that we need to do is inferential statistics, which basically allow us to say that what we found in the sample we tested would also be true of the rest of the population that we didn't test. Now, you will never have to calculate what an inferential statistic, but you need to understand what they mean. So they allow us to determine statistical significance. So what that means is when we do a particular study, we expect there to be a level of significance of less than 0.05. That means less than a 5% chance that the results were due to chance. So in other words, if the research was repeated 100 times, 95 of those times we would get the exact same results. If the significance level of 0.07 is obtained, or 0.06 or 0.08, this is too high and basically the results are not valid. You will never have to actually calculate this number. You put your results into a computer and it spits out a significance level for you, and it's called a p-value. You just need to know that we want a p-value of less than 0.05 in most studies. In some studies, we expect less than 0.01, which means that we can be 95% or 99% sure that the results are true of both the sample and the population. I will spend a lot of time on this in class because it's actually a really difficult concept. Today, just ensure that you actually get the notes down. Depending on our p-value, will depend on what kind of conclusions we can draw about what the actual results mean. And we can only generalise from the sample to the population if our results are found to be statistically significant. And this will then determine whether our prediction was either supported or rejected. You also need to know about ethics, of course, and there are all the ethics that are listed there, and each study that we come across we will link back to ethics and talk about what this means, but these are the key ethics that you need to know, and I'm sure you can already relate some of them to some experiments that you've heard about. An ERA is an empirical research activity, but this is basically a report that researchers or psychologists write. So when they've done research, they're expected to produce a lab report, and that basically is what gets published in a scientific journal. And it needs to have all of those areas that are listed there. So a title, an abstract, an introduction section, a method, which is basically the recipe, the results, which is all those statistics, so both descriptive and inferential, a discussion, and then a list of references as well. And we'll go through this really quickly in class. And that is it. Research methods done and dusted in terms of notes, but lots of stuff that we'll do in class to ensure that you actually understand these notes. So I'll see you in